Hey guys, I want to put together a quick video for you guys and talk to you all about the stuff that we talked about in class on Monday. Remember, all we got through in class on Monday was section R.1 in your book, and we didn't even cover that entire section. So as you guys are reviewing, hopefully you guys, as you all were going through class, you marked through some of the things that we skipped over. We did begin with just section 1 of R.1, and we were talking about different types of numbers. And we did discuss, knowing the difference between whole numbers and integers. Integers includes both whole numbers, but also positive and negative numbers. And so, since we were talking about negative numbers, I wanted to introduce you guys to some operations with positive and negative numbers. So we started talking about how, what happens if we have two integers, looking at, say, right now, two integers with the same sign. We started with the addition rule, if you guys remember. So if I'm adding, say, 5 plus, I don't know, let's say 5 plus 4, we know that 5 plus 4 is 9. That is because what we're also looking at here on the screen is just another way of saying positive 5 plus positive 4. Those plus signs obviously do not have to be written down for it to indicate a positive number. So that's what we're seeing when we see just 5 plus 4. So 5 plus 4 being 9 means that positive 5 plus positive 4 is positive 9. So what you're seeing here in this rule is that a positive plus a positive equals a positive. The same thing is actually going to happen when we see negative integers. That when we have a negative plus a negative, we're also going to get a negative. I mentioned to you guys in class that when we're adding integers, a great way to kind of relate to it is to think about integers in terms of money. We talked about positives being money that we have and negatives being something that we owe. So in that first example, if we, I'm just going to kind of highlight this here for us. So if we have, up here, if we have $5 and I have another 4, then that simply means I have a total of 9. Whereas in the bottom example there, in highlighting that one, if I owe $5, again, negatives being something that I owe, and I owe another 4. So say I'm checking out at a store and one item is $5 and one item is 4, then that means I owe a total of $9. So that's another way to think about these integers and when we're adding them. So we have two different addition rules, and one said that when we're adding two integers with the same sign, we simply just add them together and keep that sign, just as you guys can see what we did here on the screen. So when we have integers that are opposite signs, so say we use the exact same numbers, let's say negative 5 plus positive 4. Now things are a little bit different. In this situation, I owe $5 for something and I have $4 in my pocket, let's say. What that means is I don't have enough money. I'm short $1. So I still owe another 1 if you think about it that way. Whereas let's say that we take the reverse of this situation. Positive 5 plus negative 4, and again, sometimes you may see it written this way, parentheses just used to separate that operation sign from the integer sign there. In this particular situation, I have $5 and I owe 4. Because of that, I'm going to leave that store still having $1 in my pocket. That's an E. In that particular situation. So what we're seeing here, when we're adding together two integers that have opposite signs, my rule for that was to simply just take the difference in those two numbers. So in both cases, 5 minus 4 was 1. So that's the difference between those two numbers. However, that answer, the sign of that answer is we're going to keep the sign of the larger value. So in both of these cases, we know that 5 is a bigger number than 4. And so since in that top example, 5 was negative, that's why the answer was negative. And then in the bottom example, since 5 was positive, the answer was positive. And it doesn't matter what order your question is in. If I have, say, just given another example very, very similar to that one, if I have, say, -2 plus +8, again, my rule is to simply take the difference in the values, since, again, they're opposite signs. One's a negative, this is a positive. So because of that, we're going to take the difference in the two numbers. So we know the difference between 8 and 2, we know would be 6. And we're simply going to keep the sign of the larger value. Since 8 is my larger value, that's why 6 is going to stay positive. So my answer here would just be 6, or +6. Let's see, just given another example just to make sure we get this particular rule down, as I think addition rule number 1 is a little bit easier because we're adding it like we always do. But what's different here is, again, the two different signs. So if I have 10 plus -15, again, opposite signs. This one, 10 is a positive, -15 is a negative. So because they're opposite signs, we're going to take the difference in those two values. So we know the difference between 10 and 15 would be 5. But in this case, since my larger value of the two, this one right here, is negative, so is my 5. Again, you can always think about that in terms of money. If I only have $10 when I owe 15, I still owe another 5. So that's another way to think about that addition rule. So that's what happens when we're adding. What happened when we were subtracting, the easiest way to remember subtraction, we talked about this in class, was to remember the phrase add the opposite. As silly as that sounded, it got a little bit more complicated when we were subtracting. So what we could do was just turn it into addition. And since we were familiar with the addition rules already, we didn't really have to add another rule. We just remembered our addition rules. So what happens is when you have let's say any subtraction problem, let's say 12 minus -6. In this particular case, what we can do, and no matter what your integers are, just anytime you see subtraction, we can simply just turn it into addition. So I'm going to let me change the color of my marker here. We can change that subtraction into addition, and in order to do so, we have to change the second integer to its opposite. So the opposite of -6 would be +6. That's what I mean by opposites. So now we just go back to our two addition rules. In this case, we're adding a positive plus a positive, so that's addition rule number 1, which says we're just going to add those together. Positive plus a positive, remember, equals a positive. So in this case, we are going to get +18. In another example, let me just show you guys this one. If I have let's say -3 minus -8. Okay, same thing. No matter what your integers are at the beginning, pay no attention to them. Just anytime you see subtraction, let's go ahead and remember the phrase add the opposite. So change subtraction into addition. Change the second integer, always the second one, never the first. Change that second integer from from whatever it is to its opposite. In this case, -8 is going to become +8. So now when we take a look at this, our two numbers we have in this addition problem are opposites. One's a negative, and now this one's now a positive. So because of that, we're going to approach that with addition rule number 2, which says to take the difference in these two values. I know that that's going to be 5. But because 8 is a positive, 8 was my bigger value, and since 8 is a positive, so is my answer. So we get +5 as our answer in this case. So that was our rule for subtraction. Just again turn it into addition, and once we have those addition rules down, we have subtraction down as well. Multiplication and division were a little bit simpler in that we're always going to multiply and divide the same way that we always would. What we're going to do is simply just take a look at the two signs in the problem, and whatever the signs are in the problem, if the signs are the same, then our answer is going to be positive. If our signs are opposite, meaning one's a positive, one's a negative, then our answer will be negative. That's the only time you get a negative answer. So what I mean by that, in looking at a couple examples, let's just say I have 9 times 5. And remember, guys, we're writing this way because a lot of times in algebra, that time symbol that we are used to using to say 9 times 5, that symbol right there can sometimes be mixed up and be thought of as X, which we'll later talk about solving for x, or we did a little bit last class, but in solving for x and that kind of thing, that particular variable. So because of that, that's a lot of times not used. So the most common way to write multiplication in algebra is to simply put the two numbers next to one another. If they're two numbers, then we use parentheses. A little bit different than, remember, if we have, oops, let me switch my pen here. If we have, say, 9 plus 5. In that case, the parentheses are used just to separate the symbol from the operation from the integer itself. So this still just says 9 plus 5, so my answer would be 14 on that one. But in the one above, since there's no operation symbol next or between those two numbers, we know to multiply. So what we have here is a positive times a positive, and because we have a positive times a positive, then my answer will be positive, and we know that 9 times 5 is 45. Whereas if even same thing if I had 9 times negative 5, or I'm sorry, negative 9 times negative 5. Again, because the two integers are actually the same, one's a negative, the other's a negative, because they match, my answer is still positive 45. The only time, again, that you get a negative answer in a multiplication problem is if your signs are mismatched. If I had negative 9 times positive 5, or vice versa, if I had positive 9 times negative 5, same thing, we would get negative 45. So see, we're still multiplying it the same way we always do. 9 times 5 will always be 45. The only thing we need to make sure we're paying attention to in multiplication and division is to look at the signs. Same sign, positive. Opposite signs, negative. And again, that rule goes for the division as well. And a common way to write division and multiplication is to write them what looks like fractions. That if I have, I don't know, let's say 50 divided by 5, you might see it that way. And again, we know that that's 10, but it's a positive divided by a positive, so because of that, they're the same sign. We'd get the same answer if it was negative 50 divided by negative 5. Still be positive 10, because they're the same sign. And again, if we just have mismatched signs, positive 50 divided by negative 5, opposite signs, means negative answer. But it's still 10. It's just the only thing is, well, it would be negative in this case. And those are our rules for integers, and we talked about that because that's going to come up a little bit later in the chapter. We didn't really have a chance to do too much with those integers, more so when we get into linear equations and such in the next section, or in the next couple sections, I guess. We may come across chances or some situations where we have to apply those integer rules, and they even came up maybe a few times in the order of operations, where we had to consider those operations with integers. So that's why we touched on that at the very beginning when I was telling you guys about integers. So that was something that I would consider, and you may see on next week's quiz, just a few operations with integers to make sure we feel pretty comfortable with it. In section 2, in R.1, we talked about using inequality symbols. These goofy looking symbols that we probably saw lots of times when we were kids, when we were in grade school. We use these less than, greater than, equal to, less than or equal to, greater than or equal to. And the way that you guys will see those as of right now, we're simply just using those to show the relationship between two numbers or two situations. Whereas if I said, the number, let's say 35 is what compared to negative 6? Well, we know 35 is a lot bigger than negative 6, so we use a symbol greater than. And again, remember, alligator's always going to eat the bigger number. As silly as that sounded, it made sense. So that it just is used to complete those number statements. Let's say, given another example, if I gave you guys a situation where I said, maybe I use our integers. Let's say I have, positive 5 plus negative 14. And I want to know what that is, so is what, compared to, let's say, negative 8. Okay, so we might have to think about this for a little bit. And looking at this operation over here on the left side, positive 5 plus negative 14. Thinking about those integer rules again, a positive plus a negative, opposite signs. So we're going to have to take the difference in these two values, which we know would be 9. But because our 14, the larger value in this case, was negative, so is the 9. So really this question is asking for the relationship between negative 9 and negative 8. And so what's going to happen here, negative 9, even though 9 itself is bigger than 8, negative 9 is actually smaller than negative 8. That another way to kind of think about that, remember, think of negatives as money that you owe. So if you owe $9 compared to if you owe $8, in the first situation, the owing $9, that means you have a lot less money. So because of that, the symbol that would be used in this case would be negative 9 is less than negative 8. And so you might see situations like that where we're just comparing the relationship between two different sides. And you might see some situations like that. So that's what we talked about there. We skipped over table R-3 on page 4. We didn't get into that. We're not going to get into too much with the graphing. Same thing with section 3. We skipped over finding the union and intersection of sets. We're not going to deal with that. We did talk about section 4 in this chapter on page 7, looking at absolute value. Remember, guys, the absolute value, by definition, if I'm asking for the absolute value of something, you're going to see these little brackets. And so the absolute value of any number, I can put, let's just say 5. If I'm looking for the absolute value of 5. And I'm using this one, it's the example on page 7 itself. So if you're following along in your book, that's right there at the beginning of that section. What absolute value means is the distance from 0 on the number line. So if I'm looking at a number line, again, looking at where 0 falls, and then 1, 2, 3, 4, 5. I could go on forever. And then same thing going the other direction, negative 1, negative 2, negative 3, negative 4, and then negative 5. And we could keep going, but we're going to halt there. So the absolute value of 5 is its distance from 0. And if we were to look at that, number line here, here's 5. And here's 0. So if I counted the number of spaces, I'm going to move 1, 2, 3, 4, 5 to get to that. So actually the definition, like I said, not the definition, but the absolute value of 5 would be 5. And just as it shows there in the book too, I'm actually going to get the same answer for the absolute value of negative 5 because it's the same distance away from 0. Here's negative 5 down here, so I'm going to go 1, 2, 3, 4, 5 spaces. So the absolute value of negative 5 is also 5. So another way to think about that is all you need to remember is the absolute value of any number is simply just that number, but it's not positive or negative. It's just that many spaces away. So when you see questions like that, you might see, I might even ask, not just ask you guys easy ones where if I said the absolute value of negative 84, you guys would tell me that that was just 84. You may see operations with absolute values too. If I said the absolute value of, let's say, how about negative 10 minus 5, then let's say plus the absolute value of 3. Let's take a look at this. So in that first bracket, I'm looking at the operation negative 10 minus 5. Remember our subtraction rule. We remember the phrase add the opposite. So we change subtraction into addition, change that second integer to its opposite. So positive 5, the opposite would be negative 5. So really, this question is asking us the absolute value of what is negative 10 plus negative 5? Negative 15, right? Same sign. When we're adding those together would give us that same integer, same symbol for the answer. Absolute value of negative 15 plus the absolute value of 3. Well, remember the absolute value of any number is just that particular number without any sign on it. So this same question is asking us, what is 15 plus 3? Without the absolute value symbols on there, we see that we just have 15 plus 3, which we know is 18. So that's the answer I'm looking for. And so you can solve those problems just like that, just by remembering that the absolute value of any number is simply just that number. So there will be some questions just as simple as that. We did not, at the very bottom of page 7, I said don't pay too much attention to the ones that you guys have down there where it says removing absolute values and it shows like the square root of 3. We got into a little bit of square root, but it's just trying to have you guys simplify those, and we didn't get into anything that extreme, not just yet. So maybe a little bit later, but not just yet. So, moving on, as we get into the next section, we're getting into the order of operations. Don't forget the order of operations. We had a little phrase to remember the letters for each of these. To remember the sentence, please excuse my dear Aunt Sally. A sentence that was put together that helped us to remember just those letters, PEMDAS, as you guys see on the screen. Again, what those letters simply stand for, P. Anytime you have an operation that has multiple things happening at one time, P, you're looking for anything inside parentheses. So, for example, if you have like this inside a parentheses, remember not to be confused with when we said something like this, where this says 9 times 5. Simply the number 5 being inside of parentheses doesn't mean you have to solve that first. Whereas the problem up above, these are two separate problems. If I had 9 times 5 plus 4, we have to solve the 5 plus 4 first before we multiply it by 9. So keep that in mind, that parentheses must always happen first. So we're going to look for parentheses. If we don't see any parentheses, then we're going to move on to E. E, we know, stands for exponent. So exponents, again, meaning when we have something, oh, whoops, I need my pen. When I have like 4 to the power of 3, we talked briefly about exponents in this section, that anytime you have a number with another number in the upper right-hand corner, that smaller number is called the exponent. The bigger number, in this example, 4, 4 is what's called the base. So when you have an exponent attached to a base, you simply just multiply the base that many times. So 4 to the power of 3, sometimes called 4 cubed, in this case, anything raised to the power of 3, we can call that cubed. Anything that, so in this case, 4 cubed means that I want to take 4 and multiply it 3 times. So not to be confused with 4 times 3, as 4 times 3 we know would be 12, but 4 to the power of 3 is 64. So that's what I'm looking for here. So keep that in mind as you guys go through different problems too, that the second step you're looking for is exponents, so they all need to be solved second. So if you have multiple things taking place in a problem, like if I have, let's say 3 plus 5 to the power of 2 minus 8, something like that. Again, before I take 3 plus 5 in this scenario, I can't do that because addition doesn't come until a little bit later. The exponent has to happen first before that happens. Again, you can see here in this problem there are no parentheses, so there's no parentheses to have to solve first. So we're moving on to the exponent stage then, and that would be 5 to the power of 2, and anything to the power of 2, you guys know we oftentimes called that squared. So 5 squared would be 5 multiplied twice. Remember, that's the same thing as this. I'll write that down underneath. So we need to solve that first. 5 multiplied twice would be 25. So this problem actually says 3 plus 25 minus 8. Now, the next step we know is multiplication and division. As I mentioned as we were going over this, they go hand in hand. So we're reading that from left to right, and whichever one comes first, multiplication or division, we're going to solve that first. But there are no multiplication and division problems in this case. We only are left with addition and subtraction, which is our very last step. And just like multiplication and division, they go hand in hand. So we're reading this from left to right, and whichever one comes first, we solve that first. And in this case, it looks like addition is going to come first. We have 3 plus 25, which we know is 28. And so the last step would be to take 28 minus 8, and we know that the answer to that is 20. Sorry, I'm running out of room down here. So that's our order of operations. To make sure we're following that as we go through all of our problems, make sure no matter what, we're always applying that order of operations. And that will come in multiple times as we go throughout this book. Our next section, section 7, we were looking at how to simplify algebraic expressions. So simplifying algebraic expressions, we did a number of different things, and I think I briefly mentioned to you guys, when we have any type of algebraic expression, I know we kind of, in class, we talked about those properties that are there on pages 10 and 11, and that those are there for us to remind us as we go through the simplifying different ways that we can approach the simplifying of algebraic expressions. And so we talked about how if I have something like x plus 4 is equal to 12, and I can't remember if we had a lot of time to talk about this, but I do want to go ahead and bring this up. X plus 4 is equal to 12. Now this is something that we might be able to do in our head, but to show you guys how we simplify anytime it's not as easy as this. No matter what you're trying to do is solve for an equation, or this problem here that says x is equal to something. You want to know what that something is. Obviously, when you're looking at this, you guys might be looking at this and say, well, whatever something plus 4 is equal to 12, well, that's 8. Again, they might not always be that easy. So let's see how we do that. What happens is, since I want x to be by itself, thinking about this equal sign, imagining there's kind of an imaginary dotted line going down here, and I want over here on the left side, so let me highlight this. So over here on the left side, right now, x is sharing that side with this 4, and I want it by itself. So what I have to do is I have to get rid of this 4. And how I get rid of a number is I do the opposite of what's being done in that case. So right now, 4 is being added to x. So the opposite of addition would be subtraction. So I'm simply going to subtract 4. And what happens here is, because the opposite is happening, plus 4 minus 4, they're going to cancel one another out. And that leaves me with x down here, and that's exactly what I want. But remember what the equal sign that we have there between our sides, remember what equals means. Equals means that this left side is equal to the right side. So anything we do over here to the left side, like subtracting 4, we better do the same thing over here in order to keep it equal. So we also have to subtract 4 over on that side. And again, over on the left, what happened in these two situations, these two, again, the 4's had canceled out and left me with x. And then over here on this side, 12 minus 4, nothing cancels out there. It's just a subtraction problem. So I have 12 minus 4, which we know that is equal to 8. And I'll just cover up that question mark there. We know that then x is equal to 8. And we'll learn later as we talk about some of these a little bit more. What you can do is, what you can apply a little bit later, you can apply substitution, meaning you can go back to the original problem, which said this, and whatever you got as your answer, that means if you substitute that answer right into that original problem, you should have a true statement. And this statement that says 8 plus 4 is equal to 12, well, we know that very much is a true statement, so therefore our answer was correct. So no matter what you have going on, so say if another situation takes place, remember how we get rid of things is we do the opposite. So if I have, say, 5x, in this case, 5x simply means 5 times x. Remember, you can just write numbers right next to each other and it means the same thing, or it means multiplication in algebra here. So the coefficient 5 written next to that variable x means 5 times x. So if I had 5x is equal to 20, again, in your head, you guys are probably thinking, well, I know 5 times 4 is 20, so this is obvious. Again, they might not always be so obvious, so we can solve equations the way we know, or solve for x here the way that we know how. We have to get rid of that 5 because the idea is to get x by itself on one side of the equal sign, and right now x is sharing that left side with 5. So let's do the opposite to get rid of that 5. 5 is again currently being multiplied by x, so I have to do the opposite and divide by 5. That 5 over 5 is the same thing. If you guys may or may not remember what happens in fractions when you have a number on top of another and they're the same, that's equivalent to 1. So therefore they're canceling each other out, leaving me with the x that I want over here on the left. Again, to keep it equal, I have to do the same thing I did on the other side. So I'm going to divide by 5, just as I did on the left. I'm going to do that on the right. And we know that 20 divided by 5 is 4. And so therefore x is equal to 4. Again, you can use substitution to check our original statement. 5 times 4, is that 20? Absolutely. So we know that we did that right. Another thing I talked about in class on Monday, in these types of algebraic equations, if you have two things being done to x, what you want to do, like for instance, if I have, let's give kind of opposite of what we looked at so far, if I have x divided by 4 minus 3 is equal to 10, then what this is saying here is some number, if I take that number and divide it by 4 and then subtract 3, I get 10. So what I'm going to need to do here is I'm going to need to get rid of two things. I need to get rid of, again, because the idea is to get x by itself so that the statement says x is equal to some number. So I've got to get rid of those two numbers on the left so that I can get rid of, or so that I can get x by itself. Anytime two things are being done to x, you have to think kind of in the opposite of the order of operations, meaning that I'm going to get rid of whatever's being added or subtracted first, and then I'm going to get rid of whatever's being multiplied or divided. And in this case, 4 is being divided and 3 is being subtracted. So I want to get rid of that 3 first. So again, and how we get rid of numbers is I do the opposite. So I'm going to add 3, and I'm going to make sure I do it to both sides as we've done so far. 3's are going to cancel out over here, and just to kind of show you what I have right now, we haven't done anything with the 4, so I'm left with x over 4 still. And then over on the other side, 10 plus 3 is 13. So all I have is just another statement, and I have to just do another step. It just becomes a two-step problem. And in this case, so now I'm left with just x divided by 4 is equal to 13. So the opposite of dividing by 4 would be to multiply by 4. So I'll do that there, and 4 over 4, since they're opposites, I'm going to cancel those out, and that leaves me with x, what I'm looking for. And then to do the same thing on both sides, I have to make sure that that happens. I'm going to take 4 times 13, and 4 times 13 gives me 52. So get 52 as my answer. And so therefore x is equal to 52. Even probably more so important to double check your answer using substitution. Again, the original problem was x divided by 4 minus 3 is equal to 10. So let's use that substitution and plug in there. If I go ahead and substitute there, take 52 divided by 4. 52 divided by 4 is 13. And then, so my statement now says 13 minus 3 is equal to 10. Is that a true statement? Absolutely. So that means 52 was correct in that problem. So that's how we can solve for x. And what it also covers there on pages 10 and 11 are different properties that talk to us about, I'm not going to, when I quiz you guys on things, I'm not going to quiz you all on different properties. Like, I'm not going to ask you guys what's the commutative property of addition. The purpose of that is just to show you that addition can be rearranged if ever need be when we're trying to solve for an algebraic problem. So if I have, say, 5 plus 3, then I know that that's the same thing as 3 plus 5. You know, that's what that property tells us. Multiplication has a commutative property as well. We know that 4 times 2 is the exact same thing as 2 times 4. So only addition and only addition and multiplication have that particular property. And so that's what these are showing. The main thing we focused on in class on Monday was the distributive property. So I want to show you guys a few things about the distributive property. Okay, so the distributive property says that whenever you have something outside of a set of parentheses that's multiplying by those numbers inside the parentheses, so say if you have, I don't know, I'll start with something easy, like say 4 times 3 plus 2. You know, obviously we could look at 3 plus, the order of operations and say 3 plus 2 is 5, and then 5 times 4, this should be 20. But the distributive property says this, that what you could do is you could distribute what's outside of the parentheses to what, to each number inside the parentheses. So meaning like you could take that 4 and distribute it to the 3 first, and 4 times 3 we know is 12. And then since the operation inside the parentheses is plus, it would be plus, and then 4 times 2, which is 8, and 12 plus 8 is, is 20. So that's just what the distributive property says. So very similar to all these other commutative properties and associative properties, and that all of these are going to help us when we go to simplify problems a little bit later on. So that being said, that helps us when we get to equations that have variables in it. Since we don't know or I should say expressions, expressions that don't have an equal sign, that don't have equal to something on the other side. So say something like, if I have, I'm going to start with kind of an easier one. If I have, instead, let's say I have 4 times 3x plus 2 this time. A little bit different. Since I don't know what x is, I can't really do anything with that. So when I go to use the distributive property, if I want to simplify this and try to get rid of the parentheses, what I can do is I can use the distributive property, which says that I can take 4 times 3x, which would be 4, oh, no, not 4. 4 times 3 we know is 12, so that's going to be 12. But x, because that x, we can't do anything with something we don't know what it is. It's an unknown number. And then we're going to say that's plus, because that's what the operation is in here, plus, and then we will distribute the 4 to this side now. 4 times 2 we know is 8. So we get 12x plus 8. And that's just an equation, an expression, since I don't know what that's equal to, since nobody has told me what x is equal to just yet. That is as simplified as it's going to get. So if you're ever asked to simplify something, a lot of these properties are going to help in the process of simplification of these things. And we'll get into that into a little bit more detail a little later on. So it's helpful and it's good to know, and we'll probably touch back on these different properties as we go through lots of different examples throughout this class. So it's good to be familiar with these different properties. And then the last thing we talked about in class was algebraic models. When you get to certain word problems, you can take how word problems are given to you, and you can take them and turn them into an algebraic model. And so you guys would probably see more like the ones that you have at the bottom of page 12. Letter A, it says the maximum recommended heart rate M, so they're going to call M, that represents the maximum heart rate, so we'll call that max heart rate. That's what that M represents. For adults is the difference of the number 220 and the person's age. So 220 and the person's age, and they said let's call that A. So the difference, meaning taking that and subtracting A, age. So it wants you to write an algebraic model for this statement, for this sentence. You can take that and turn it into an algebraic expression. So writing that just kind of word for word is that means that the maximum heart rate should be, and I'm going to use equals because that's how you could write, it should be or equal to 220 minus a person's age. So that way, if a person is, say, and later we'll talk about substitution, and you could say, oh, okay, well, what if the person is 52? Then you would take 220 minus 52, and their maximum heart rate is 168. You could solve that. If you say, oh, well, person is 67. Okay, well, 220 minus 67, their maximum heart rate should be 153. So we can use that a little bit later on, but right now it's just taking different phrases and being able to turn it into a model. You probably wouldn't see one like letter B, as that one was a little bit more complex, at least not just yet, not the very first day. So those are some of the things that we touched on in class. I hope that kind of reminds you, going over those things and helps you with some things that you guys might see on the first quiz, but that's about it. If you guys have questions, you guys know, you guys can reach out to me anytime. Thanks, guys.